In Chapter 5, we are going to explore statistical concepts. So some terms that we are going to use throughout our conversation about statistical concepts are, first of all, statistics. And this might be a bit of a scary word, but it's just the idea that we would use mathematical concepts to learn more about a group of people or certain type of information. So we'll talk about different kinds of statistics throughout this chapter and throughout the course. So then we have what's called descriptive statistics, which just helps us to learn a little bit more about a certain body of information. And so these don't necessarily make any kind of assumptions about anything. These just help us to learn about the type of information that we have. Frequency, which is looking at how often things are happening and how regularly things are happening, and then looking at the distribution of different kinds of statistics, frequency of different kinds of data that we would use, and we would use statistics to learn about frequency. Inferential statistics are used to determine relationships between different types of information. So we'll talk about things like correlation and regression later in this chapter, and those are examples of those inferential statistics. A sample, which is the group of information or group of people potentially that you are specifically looking at in your research or in your assessment procedures. So a sample might be the clients in your setting. They might be the students in your school. So these are the specific people or types of information that we're looking at in what we are doing. Then there's the population. So that's the whole. So for example, in a school setting, a sample might just be certain types of students that we would look at. So maybe we are just looking at a handful of students that were referred to us, or we're just looking at fourth graders. And the population would be all of the students in the class, for example, if we're just looking at what's going on with one or two students, or might be the entire school and we're just looking at the fourth grade classroom. So the population is the whole group. And then variables are the different things that we might look at. So these are different constructs, different types of information that we might be looking at. And so variables might be, symptoms. Variables might be intelligence tests. Variables might be different indicators of what's going on that we would look at potentially in relationship to each other. So we talk about types of scales. So different ways to measure and talk about different kinds of information, different kinds of variables. And so these are different than when we talk about scales being subscales of an assessment. These scales are in reference to types of variables that we might look at. So there are nominal scales, which are just qualitative and provide identity. So these are like a list of names or a list of words, gender identities, those kinds of things. So these don't necessarily have any kind of relationship to each other. They're just meant to identify. Then we've got ordinal scales. These are similar to nominal scales because they talk about different kinds of information that don't necessarily have specific relationships to each other. They're really meant to help us rank different kinds of variables. And so these would be rank order, but the difference between like 1 and a 2 isn't necessarily the same. So we're just ranking things, but not paying attention to the intervals between them. So a great example of this is what's called a Likert scale, which are used in a lot of different kinds of assessments. So like on a scale of 1 to 5, 1 is not so bad, 5 is terrible. How do you feel about statistics? And you would pick from 1 to 5. But I'm not really concerned about the difference between a 1 and a 2 and a 4 and a 5. I just want to know generally how you would rank your feelings about statistics. So then in interval scales, we are focused on the difference between a 1 and a 2 and a 4 and a 5. So it's important that the different numbers that we would use to measure magnitude are equally spaced. So think about things like temperature, where the difference between a temperature of 45 degrees and 46 degrees is the same as the difference between 85 degrees and 86 degrees. So 1 degree difference is the same regardless of the temperature. And in an interval, there's no absolute zero. And so with the temperature example, that might be a little confusing because there is 0 degrees or negative degrees, but there are negative degrees of temperature, but there is no absence of temperature. So even when it's negative degrees outside, there is still a temperature. It does still exist. It's just really, really freaking cold, right? So then in ratio, we're still ranking by magnitude, but there is a concept of zero, which is the absence of that thing. So for example, age. Like if you have an age of 0, you either aren't born yet or you don't exist. If you have a height of 0, there is no height at all. So there's that idea of an absolute 0. So there is the sense of an absence of that thing to begin with, and then we're measuring how much it grows from that point of absolute 0 in a ratio, as opposed to an interval where we're more worried about the difference between each rank on that magnitude scale. So getting into talking about descriptive statistics, this type of statistic really looks at the distribution of a set of scores. So this might be a set of scores in a battery of tests. This might be a set of scores among a group of individuals who took the same test. But we're looking at the distribution of those things. So most often we're going to be looking at the distribution of scores among a group of individuals who took the same type of test. So in terms of frequency distribution, we would look at how these are ranked in terms of each individual variable. So we would look at how often individuals experience a certain type of symptom or how they did on an aptitude test. So we would look at each individual variable in terms of frequency distribution to understand generally how often each type of score or each outcome was happening amongst the group in the distribution. So then group frequency scores, we would specifically look at group ranges of these scores. So as opposed to looking at discrete variables, which would be one variable by itself, we might look at group variables when there are a whole lot of different types of information that we are looking at and we want to consider it all together. We would use what's called a group frequency distribution, or looking at the changes among different groups of variables or scores. So when we're looking at distribution data, we are often going to use some sort of visual representation of that data to help make sense of it. And so we might use different kinds of graphs. So your book gives you some example of different kinds of graphs, but I want to talk specifically about curves and skew and looking at central tendency. So these types of curves are really looking at central tendency, which is looking at average, which is looking at how often things are happening. And so we might represent these on a curve to look at overall how the scores are distributed among the group that we're looking at. So we have what's called symmetrical, which is an even or a normal curve, which means that things are falling in a way that is pretty typical. So at the height of the curve, we see what would be the average, meaning that most people's scores kind of fall in this central area, that central tendency idea. And then there might be some that do worse than average and some that do better than average, but most everyone falls in the middle here and are pretty well averaged. We see this a lot in terms of things like intelligence testing. So then we have what's called an asymmetrical curve, which is skewed. So you might hear this term skew quite a bit in statistics, and that means that either we have a positive or a negative skew. And that means that a negative skew, most everyone did pretty well, and then there may be a few people who did exceptionally badly. And so it's a little misleading in the terms, but the negative skew means that there are a couple of folks who got especially negative scores, which are bringing down the group average. And then in terms of positive skew, most everyone had low scores, and then there were a few that had pretty high scores that are bringing up the group average. And you may think that like a negative score might be a bad thing, but there are certain types of assessments where a negative score is a desirable thing. So for example, if you're measuring symptoms of something, you would want a negative or a lower score because it means you don't have as many symptoms. So it's not always necessarily a good thing or a bad thing to have a type of skew. It's just important to understand in terms of your typical data that you have most everyone falling in the same sort of area and just a few people who had an exceptionally low score or an exceptionally high score, which means that there's a skew. So what this means in terms of understanding data is that the average might be pulled a little bit lower than it really would be or pulled a little bit higher than it really would be just because of those few scores that are exceptionally high or exceptionally low on the scale. So it's just important to understand how this works, because if we're just looking at the average score of something, we may not have the full picture of what's going on. So we have to look at these measures of central tendency to understand how the scores are overall distributed and the relationship between them. So then we have this concept of kurtosis, which is the peakness or the flatness of the distribution. So you see these kind of in a way align a little bit with the skew, but they tell us different types of information in terms of how the scores are falling on the whole. So we have those mesokurtic kurtosis in the middle, which is like this normal curve where about an expected number are falling in the middle, and then we have a pretty typical distribution on the higher and lower end of things. Then we have the leptokurtic kurtosis, which means that a whole lot of scores are kind of grouping together in the middle. So we see a lot of scores that are pretty similar and are pretty close together. And then you have this platykurtic kurtosis. Say that one 5 times fast. So this one shows us that a lot of the scores are pretty well distributed. There's not really a common average. There aren't a lot of common scores. People's scores are pretty well distributed, not in a way that would be average, but meaning that very few people are getting the same score. And so looking at things like kurtosis might tell us, for example, information about the reliability or validity of an assessment that we're using, or how individuals are experiencing those assessments. So again, it's important to get that context of how things are falling within the group, because if we have more of a platykurtic kurtosis going on, then maybe our assessment is not necessarily capturing the information that we want it to. Same with a leptokurtic kurtosis. For example, if everybody's just doing super well on an assessment, it may not be an accurate measure of their aptitude for that particular information or achievement in that particular area. It just might be that the assessment's too easy or something like that. So we're looking at both the skew, which is the central tendency, or the distribution of data, as well as the kurtosis, which is the peakness or the flatness. So then in terms of central tendency, there are some different descriptive statistics that we would use to understand the overall picture of the data among the group that we're looking at. So there's the mean, which is the average value. There's the median, which is the middle score. So if we lay them all out in rank order, the median would be the one that falls in the middle. And then the mode, which is the most common score, and this might be bimodal or multimodal. So there may not be necessarily one score that's most common. There may be a couple of scores that are pretty common. And so there might be, for example, a lot of folks who did particularly well and a lot of folks who didn't do particularly well on an assessment. And so there might be more than one mode, one falling pretty high on the scale, one falling pretty low on the scale. And so when we're putting these things together, looking at the overall curve, the skew might impact the mean or the average. The skew might also tell us about the median of the scores. So the median might be changed based on the highest or lowest score, And then we would look at the relationship between the mean and the median to understand the type of skew. So in the visual here, we've got a negative skew, which would mean that the mean is lower than the median, versus a positive skew where the median would be higher than the mode but lower than the mean. So it's just telling us a little bit about the relationship between those three. And then we would look at kurtosis to tell us about the mode, because the mode is always going to be at the top of the curve. That's always the most common score. So looking at those different types of kurtosis, like a leptokurtic kurtosis, means that the mode is the score that most everyone had. Everyone had a pretty common score, as opposed to a platykurtic, where the mode might be every single score because everyone got a different score. So again, just looking at the relationship and the central tendency of the data as we look at it in a whole. So now we talk about variability. So we looked at the central tendency of the data. Now we have to understand the distribution of the data and the relationship between data points, right? So not just the overall trend, but the difference between each one and how they are differing from the mean, or the variability. So how much each score varies from each other. So we have the range, which is the spread of all of the scores and the differences between them. The variance, which is how much each score differs from each other. And then the standard deviation, which is the average distance of those scores from the mean. So there is a relationship between calculating variance and standard deviation, and both of these concepts tell us different things about the distribution of the data. Okay, so we've been talking a lot about statistics. This may be a good moment to just take a deep breath, look at these cute pictures of puppies and kittens, maybe take a quick stretch, and then we're going to jump into some more statistical concepts. So this becomes really important in things like intelligence testing. And there's what's called a normal curve. So this, looking at the central tendency, you'll see that there is no skew to this data, and the kurtosis is pretty typical. So in this normal curve, theoretically, all the scores are normally distributed. It's what's called bilateral symmetry, which means that it's that bell-shaped curve. It's the same on both sides of the mean. So in this visual, the mean is marked by this X in the middle, which is the average. And in this case, the mean, the median, and the mode are all the same. So they all fall right there in the middle. And it's unimodal, which means that there is one common score, not multiple common scores. So again, that mean, median, mode are the same. And so we can expect that the same number of folks will fall within 1, 2, and 3 standard deviations of the mean. So one standard deviation above the mean, -1 marking one standard deviation below the mean, 2, and then 3, so on and so forth. And so being able to call this a normal curve, we can expect to make predictions based on this. So we know that about 68% of folks are going to fall within 1 standard deviation of the mean. 95% of folks are going to fall within 2 standard deviations of the mean, and 99.5% of people are going to fall within 3 standard deviations of the mean, which means that about 5% of people would fall exceptionally high or exceptionally low on this curve, meaning that they're beyond 3 standard deviations of the mean. So the way we make sense of this is thinking about, like, when you take standardized tests, they talk about your percentile. That connects to this idea of central tendency and a normal curve. And so if, for example, you ranked in the 68th percentile for your group, that means that you've fallen 1 standard deviation above the average score for your norming group. And then if you fall, for example, 95th percentile would be 2 standard deviations above. So that helps us understand where your score is relative to other scores in your norming group based on this normal curve. Okay? Beyond these descriptive statistics, which tell us about the distribution of the data, we then have these inferential statistics, which help us to understand the relationships between different kinds of variables. So in all of these statistical tests, we're not focused on just one variable, we're focused on the relationship between multiple variables. So talking about relationships, we are going to first go into correlation coefficients. So this measures relationships between two different variables. So there can be a positive correlation or a negative correlation. And it doesn't necessarily mean a positive correlation is a good thing or a negative correlation is a bad thing. It just means that as one variable increases, the other variable increases in a similar way. Or if one variable decreases, then the other variable decreases in a similar way. So if they're decreasing together, then that's a negative correlation. If they are increasing together, it is a positive correlation. And so these are measured from negative 1.00, which would be a negative correlation, to a positive 1.00, which is a positive correlation. And so we're looking at the strength of the relationships between the two and how much they move in the same way together. So a negative 1.00 is a perfect negative correlation. It's a very strong relationship. A positive 1.00 would be a perfect positive correlation, so a very strong relationship. And then anything in between, we would look at how strong that relationship is, meaning that as one variable changes, the other one changes in a similar way. So the further we drift from a 1.00 correlation, the less strong that relationship is. And so if there's not a very strong relationship, then we may not be able to say that these things change at a similar rate or are in any way connected. And be careful that we don't fall into the trap of thinking that correlation means that one thing causes the other. It just means that they happen at the same time. And one of the kind of classic examples from statistics is that in the summertime, we typically see an increase in the rate of murder in larger urban areas. In the summertime, we also see an increase in the rate of buying ice cream. So if we were to try and make a causation relationship using correlation, we could say that eating or buying more ice cream makes people commit murder. And of course, we know that this is not true. It just is likely that there's some other variable at play that is increasing both the rate of ice cream sales and the rate of murder. But if we are reading correlation correctly, we would not make that kind of assumption that one thing would cause the other. And it's kind of a silly example, but there are all kinds of examples of statistics in the media nowadays where they're looking at correlation and then trying to make a causal relationship between the two. So they might, if you really start to pay attention, you'll see this all the time in the news where they say, oh, well, these things are changing and increasing at the same rate, and so one must cause the other. And that's just not always the case based on correlation. There are other types of statistical tests that we can use to determine that kind of predictive relationship, but correlation coefficient is not one of those that is appropriate. And so we have different kinds of statistical tests at our disposal to determine this relationship. We might use a Pearson's R, we might use a Spearman's test, or we might use a phi test, depending on the types of variables that we are using and the way that we are looking at them. So your book provides some more information about these types of tests, and I'm happy to answer any questions specifically about these tests if you post them in our course page. So we would use a scatter plot to help display different types of data, looking at the relationship between the data points. And so this would help us to determine and to get a visual of the correlation between those two. And we would look specifically at the way that they cluster together or don't cluster together to help visually represent that correlation. So taking a look at some scatter plots to give you an example of some of these correlational relationships, you can see, starting from the top left, the correlation, the positive correlation of 1.00, which is a perfect correlation relationship. And you see it's positive because the scores are trending upwards together. So you can see that they all move exactly in a line. They're all connected in the same sort of way with the same distance between them. Then next to that, with this negative 1.00 correlation, again, it's a perfect correlation. The dots are all perfectly in line with each other, trending downward in the same way at the same rate. So again, it's not that everyone has the same score, but it's that they are changing at the same sort of rate in the same sort of way. So a correlation of 0 means that there is no clear relationship between these two variables at all. And so you can see on this scatter plot on the top right that they're all just kind of all over the place. There's no clear trend or relationship between them. They're just evenly distributed in different kinds of ways. And so we can't necessarily see any connection between them. They all just sort of exist on the same plane. So looking down at the bottom, just sort of medium relationships, because we see a perfect relationship in both a positive and negative direction. We see no relationship. And then there's kind of this medium level of relationship. So looking down at the bottom, we have correlations of 0.8, both on a positive and a negative correlation. And that shows that they're kind of clumped together, but not in any sort of way that lends any particular strength to that relationship. So compare this 0.8 correlation to the 1.00 correlation. In the 1.00, you see that they all are perfectly in line with each other, moving at the same rate in the same direction. With the 0.8, they're all kind of moving in the same direction, but there's a bit of distance between them, so there's quite a bit of variance in the distribution of scores here. So there is a relationship, but not a particularly strong one. And then the positive and negative, again, just indicating that they're either trending upwards at kind of a similar rate or trending downwards at kind of a similar rate. So hopefully this visual representation shows you some scatter plots, but also helps you understand this correlation idea a bit better. So transitioning from correlation, in which we cannot make any kind of causal relationship assumptions, to this idea of regression, which is another way of learning about relationships between variables. So regression is designed to determine how well one variable will predict another variable. And so this is where we can kind of start making more of those causal relationship assumptions, because one would predict another. So to pull back our example from the ice cream and the murder rates in urban areas, using regression, if that relationship really existed, then we would be able to predict how many murders that there would be in one city just based off of how many ice cream cones were sold that summer. And that is most likely not the case. And so then, given regression, we would understand that while that relationship exists, it's not necessarily one that would allow us to predict or make any kind of assumptions about those variables. So looking at regression, we are understanding how those predict each other and the relationships about different variables for that specific purpose of prediction. So we would have a linear regression, which predicts the value of one variable based on another variable. So that example of ice cream and murder predictions. And then there's multiple regressions, which are when we're working with more than one variable and wanting to make predictive relationships among a group of variables as opposed to just two variables in a linear regression model. So then we would use factor analysis, which is another statistical option to examine relationships between data when we have a whole lot of data that we want to make sense of. So we might have a large number of variables, perhaps more than we could use regression to understand, and we want to analyze a relationship amongst these really broad, large groups of variables using common dimensions. So we don't use factor analysis a whole lot in terms of testing and assessment, but we might use something like regression to understand the relationship between, for example, depression and anxiety in the outcomes of assessments for a client or a group of clients.